Okay. So I've been saying this was going to be coming, right? We've been talking about combinational circuits up until now, and what they've been lacking. What we've been lacking so far is circuits with memory, circuits that remember, right? We can't do very much with circuits. We can do a little. We can't do very much until they remember what happened before. So what we're going to talk about today is really the foundational building blocks of how do we get memory out of circuits? How do we build something that remembers a value? Now, the basic building block of this is going to be what we call a latch. And all that means is it takes a value and it latches onto it. It holds onto it and won't change until you nudge it off of it, right? It's until you give it a new value. So the basic building block that we have there of latches, there's many ways to build a latch, but one of the simplest latches is what we would call the SR latch, where SR stands for set/reset, meaning we can set the latch to 1 or reset it to 0. Now, you can build them out of AND gates, OR gates, NOR gates, NAND gates. What I'll show here is the, let's see, the NOR gate implementation first, because in a way it's the easiest one. Here we go. So this is an SR latch built off of NOR gates. The NAND gate looks virtually identical. The difference in the NAND gate implementation is the set and reset are active low. All right, so what is this circuit doing? Well, let's start by assuming that we're at some output. Let's start, we know what Q and Q bar are. So let's say Q is 0, and that means Q bar is 1, right? That's kind of the definition. If Q is 0, the other one has to be not Q, which is 1. If it's not there, something weird is going on. All right, now we can look at what happens when we don't do anything with the inputs, meaning set is 0, reset is 0. All right, so set. If it's 0, the other input is 0, right? So Q is coming back around. Now this is a NOR gate. So an OR gate would have a truth table of 0, 1, 1, 1. That means a NOR gate is the opposite of that. That we're 0 for anything other than 0, 0. Right, our output is 0 unless our inputs are both 0. So here we have 0, 0. That means our output is 1. Q bar is 1, that's good, right? That's a verification. If Q is 0, Q bar is 1. That feeds back, so this is what we kind of call this feedback or cross coupling. And now I have a 1, 0, and we know that if it's not 0, 0 at the inputs, which it isn't, then our output is 0, so Q is 0. Great. So at least we have a beginning situation for what this is doing. This is storing for us, as long as we don't lose power, a 0 on Q. Now let's go ahead and take, this was for S is 0, R is 0, set is 0, reset 0. Let's transition set to 1. Okay. So that means this was 0, right? Q is 0. It feeds back around, and now its set is 1. So it's 1, 0. That means Q bar transitions to 0. And since reset is still 0, I have 2 zeros at the input of the bottom NOR gate, and I output a 1. Now what's interesting is if I transition set back to, so I took set and set it to 1. If I transition set back to 0, I still hold this value of 1. It doesn't go away. The only way I get rid of the 1 on the queue is by asserting reset. So let's do it. So this was still 0, and now we're going to transition reset to 1. Let's look what happens if set is 0 and reset is 1. So I'm just going to flip those at the same time. Okay, so that means reset here is 1. That means we know the output Q has to be what? 0. Because if there's any 1s, the output is 0. Then Q feeds back around. Set, I said, went back to 0. Therefore, 0, 0 is 1. All right. Let's look at one weird situation where I then transition so that they're both 1. Both set and reset are 1. What happens? Well, the output of the first NOR gate is tied strictly to set and Q. But if set is 1, regardless of what the output of Q is doing, the output is 1. Similarly, the second NOR gate, if reset is 1, regardless of what Q bar is doing, the output is 1. Should it be 0? Oh, sorry, 0. Sorry, yeah. I did that reverse, 0 and 0. So we get zeros on both because of 1s. So we're no longer Q and Q bar, right? They're the same. This is okay, kind of. We're not supposed to do it. It's really treated as an undefined state. And the risk is, what happens if I deassert both of them? Meaning I take them both from 1 to 0 at the same time. We're no longer setting, we're no longer resetting. And what's going to happen is you're going to have kind of 1s chasing each other around in this circuit. And you're going to end up in what we call a metastable position. And what that means is it's like taking a card and laying it on its edge on a table and trying it balanced there. Now, it's going to end up either a 0 or a 1. It's going to get there. It's just waiting for the random processes of like the air blowing around or, other things happening where the card is going to wobble and fall. But so it's going to be a 0 or 1, and we don't know what it is. That's metastable. So the problem with set and reset simultaneously is that we can end up not knowing what the output is. We just don't know. And that's obviously a problem when we're trying to remember what it is, right? If we just don't know that definition, that's a problem. So we try not to ever do both set and reset in an SR latch. We avoid that because it causes problems. Now, in the real world, it would settle to something and everything is fine. In simulation, it's actually going to cause you a bigger headache than that, because what's going to happen is as fast as the simulation can go, it's going to alternate 0s and 1s because it's, as I kind of said, they're chasing each other around, and your simulation is just going to lock up and crash because it can't handle metastable conditions very well unless you have like a supercomputer that's designed for it. So if you build an SR latch in Vhdl and simulate it, make sure you never deassert both 1s at exactly the same time. Okay, you can also build them, as I said, with NAND gates. Let's see if I want to do this example. So we're going to see lots of timing diagrams that kind of come out of this, right? So I can do this kind of arrow notation to describe what they're doing, or you can do it as a more traditional timing diagram. I'm actually going to save it. I'm not going to do this one. I'll do a different latch shortly as the example. And part of that is simply because we don't really use these SR latches by themselves. They're too finicky and they're not as useful as some other forms of latches. So we kind of move on to, well, we'll get to the D-Latch like just about. But what we're going to first talk about is how do we make a latch in Vhdl? How would I program this if I wanted to risk crashing Vhdl? Well, let's say that we have an entity, SR, and it has ports, well, it just needs set and reset, right? And I'm going to say, for the sake of sanity, that I'm going to use the Nand Gate version of this. So I'm going to do set low and reset low. So that's what I said the difference is between the Nand Gate and the NOR Gate implementation is the set and reset are active low. So I'm adding an _L to indicate they're active low. And then I need to have the outputs Q and Q bar. Oh, I guess I should write the in as standard. And then we're going to have Q, and Q and Q bar are both going to be, well, we have a Q high and a Q low, right, for Q and Q bar. Now, unfortunately, if you look at this, Q bar is both an output and an input, right? And we know that Vhdl does not like having output on the right hand of expressions. So one way of avoiding this little issue is when we declare it, we declare it as a buffer. So that buffer allows us to kind of avoid the issue, that error that we know is coming, right? You can kind of work around by creating intermediate signals, but let's focus on using a buffer because that's the new idea for you. We would then end entity, have the architecture begin, and then you just need to say Q high, so meaning just Q, is assigned to not set.low and Q low. So it's not this, right, Nand, really. So what that means is I now have an output on the right-hand side. I'm not going to get an error because I called it a buffer, not an output. Everything's okay. I would do the same thing for Q low, but where we're imagining that I've replaced these NOR gates with NAND gates, right? So I'm dealing with that same kind of situation where it's not R low and sorry, Q high, right? If feedback around this would be a NAND gate. There we go. That's what a latch is doing. Again, it can cause issues in simulation, and I just want you to remember that because I will probably ask some question around that. In this case, because they're active low, deassert would mean going from 0 to 1, so raising it, right? And we would never want to do that. We don't want to deassert the signal and assert it as a 0. Okay. So let's talk a little bit before I move on. If I just have that SR latch, what can we do with it? So say I write in Vhdl or I build it in a circuit. Let's talk about applications. So first off, let's create a circuit symbol, schematic symbol for the SR latch. Like so. That is our representation, so we don't have to sit and draw NAND or NOR gates at all. And it also gives us a lot of flexibility on how we want to design it. So let's say I want an active low set and reset. I just add inversion bubbles at the inputs, right? Now, that's exactly what we talked about here. That matches the code. Active low set and reset, cues come out. Now, let's build one of your guys's, well, 2 switches, actually, that you've built many times now on your circuit boards. Okay, so here, they're getting pulled up to 1 by default, right? So their default state is 1, and since they're active low, that means they're both off. And we want to be able to use a switch to connect them to ground. Okay, remembering that these are our pull up resistors, that if we're not connected to ground, the resistors will pull it up to VCC. If we are connected to ground, well, it's direct ground directly in. Nothing is less resistance than RPU, so it's 0. Now, in this circuit, notice that we are always going to set or reset, one or the other. We have no 0, 0 option. This switch that I've drawn is a little different than the switches you've used before. So before, you've used what are called single pull, single throw. Single pull, single throw. SPST, meaning it's either engaged or not. What this is single pull, double throw. So it means there's one switch, but it has 2 positions. It can either be at left or right, on, off, so that it takes 3 pins, basically. Okay, so single pull, double throw, I switch it. So why would I build this circuit with the SR latch? Well, it's a physical phenomenon that sometimes we might not think of. But let's say I wanted to build a counter that simply counted the number of times I threw a switch. And this is actually something you would really do. Say you were working for a lighting company and they were doing failure testing, and they would design a machine that would just sit and throw the switch back and forth, and then they could put on their data sheet, how many times can you flip the switch before it breaks on average? That's a real job, not the most exciting job, but they exist. But we've got this little switch, and we'd like to imagine that we throw the switch and it goes close, right? But it doesn't. What happens is it hits and rebounds. And so it goes bum, 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 bum. Right? It bounces. So if I were to throw just a regular switch into here and it was counting the number of times the 1 or 0 changed, it would go 1, 2, 3, 4, 5, 6. Right? Every time it bounced would be a new output. But if you throw on the set or reset latch, the SR latch to the output of this, and I'm in the reset position right now, right? So I've connected reset to 0, it's active low. That means Q is going to be 0. Then I throw that switch to the other side to set. Instead of what happens is if I'm counting on Q rather than counting the output of the switch, it bounces and just goes set, 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 set. Which we don't care, right? That's just going set it to 1, set it to 1, set it to 1. Okay, not a problem. It didn't change. There was no connection, disconnection, connection, disconnection, because the set remembered what it was before. Does that make sense to everyone? So this is what we call debouncing. We want to do this all the time for various reasons. In circuits, you'll probably encounter some in 3610 because you don't want to count the number of switches. You don't necessarily want to flicker lights or something if you're throwing them. There could be power surges if you're about building a power circuit. So you want to debounce the circuits fairly often. This is a very simple way of doing debouncing. Okay, the next thing that we can do with the SR latch is add just a little bit of complexity to it to make it easier to use. So what we want to build now is called the D-Latch. Now the D-Latches tend to have an enable signal on them, meaning that they're only going to respond to input if the enable is turned on. So just like the other one, we start with an SR latch. I'm going to throw inversion bubbles on this, and you'll see why in just a second. And we're going to take advantage of this cross-coupling concept once again. Okay. So this is what we call a D-latch or data latch. So rather than having the options to set or reset, we can actually take a data stream, D, and save that. Now, it's kind of easy. This is why I did the inverting inputs for set and reset, is because you can see that this NAND gate and this inversion is equivalent to drawing AND gates here. Right? Those two inversions can cancel each other out. So this circuit is equivalent to the following. Right? Nice and easy to convert back and forth between universal gates or not. Now it's a little bit easier to talk about this circuit in just the AND gate. So the AND gates are just functioning as the enable gates. We can just turn it on or off with the enable, right? That's what AND gates do is, well, one of the functions we use is to add an enable to something. We can only pass data if it's enabled. Now we also have the benefit with this cross coupling that we don't have to worry about the set and reset being different. There's this kind of feedback preventing us from having issues. And then let's look at what happens really. So let's say enable is on and we want to do something with D. D passes through to the set and that means we get Q of whatever data is, whatever D is. Just like the SR latch, if I were to create a schematic of that, it's going to just look like the following. That's our D-Latch. Where the enable goes in, we have the data. And this is also what we would like to call transparent. Because what it means is that as long as the enable is turned on, the output is going to immediately reflect data. There's whatever device delay there is, but that's it. It responds as quickly as it can. So I am going to do a timing diagram on this one because the D-latches are more used than the SR. So let's say that we have enable and data. And I'm going to create some time blocks. So all I'm going to do with data is just sit and toggle it. And then with enable, I'm going to go ahead and start off low, go high, we'll drop back low here, say low until here. Okay, so here's where the understanding of what the D-Latch is doing is important. Okay, so if we start, sometimes we have to say we don't know where it starts. So it's acceptable either to make an assumption or start off with an X which says don't know, right? But let's go ahead and see if we don't know where Q starts. So I'm going to start with Q rather than Q bar. Well, enable is low, meaning it's off. Data is high, but it can't pass anything from data. So because we're not enabled, data can't get to the output on X. We don't really know what Q's doing here. In fact, we don't really know until we enable it. But once it's enabled, then it can start reflecting whatever data is. And in fact, while it's enabled, Q is just going to, Q is just going to follow D exactly. But here, at this next time, we're no longer enabled. And what that means is it doesn't respond to D, so it's going to hold on until, and this is kind of a good trick to pick up now, is identify the locations where it's likely to actually respond. So I know because enable doesn't go positive, turn on until this point, then I can't change. I hold a 0 all the way till then. All right, then it goes positive. What happens once it goes positive?
It follows D.
Exactly, yes, it just follows D. Right, and then Q is just, Q bar is just the opposite of that. And the opposite of don't know is we still don't know, right? I wouldn't fault you if you made an assumption, say, it starts at 1, I guess. And I'll try and communicate if I want you to do the don't knows. I would default to this to illustrate that you know that it's don't know, right? And sometimes I'll say, assume that it starts at 1, or so on and so forth. So this is how we use timing diagrams to illustrate what's happening with these circuits. Okay. The D-Latch in Vhdl is actually really easy. So we've seen this before, process, right? But we've done it only in test benches, really. I showed it a little bit when I first introduced Vhdl and muxes and kind of things, but now we're going to get into a little bit more. A process is your main indicator that it is sequential logic, meaning it happens in order rather than fully parallel, as is the case with combinational logic. Now, don't fall into the trap that a process does not necessarily mean it is sequential. It is actually possible to build combinational logic inside of a process. It just depends what you do. So like the mux that I showed you guys, and you can go inside of the Canvas files, notes, there's a file called mux implementations. There's a mux implementation that uses a process. So you might go, oh, that's a sequential mux. It's not. It would get implemented once you made it with the Vhdl tools, put in a real circuit, as a combinational circuit. So just because it's a process doesn't mean it's sequential, but it means it could be. If you don't have a process, it can't be. Okay, so the next thing we need with a process is different than the test bench, and we call it a sensitivity list. And that just goes in parentheses after the words process, and it's what do you want this process to react on? Basically, if something in the process sensitivity list changes, the process will run one time. Okay, so process on, well, the two things we care about are that D and enable, which I'm going to label just EN. And then process needs a begin, which we already knew from the test bench. And then we can simply say something like if, which we get to use if statements now. We didn't get to use if statements unless we're in a process, right? We can't use if in combinational. Now we get to do it, and we get to say if EN is equal to 1, which means it's an active high enable, then Q is assigned to D. And we say end if and end process.
So this is a sequential.
This is a sequential circuit. The reason it's sequential, and we know it, is it has memory. It remembers what it was before. Now, the way we know that is a little bit more complicated. So if we look at this process, D changes, right? Then the process will execute and say, if it's enabled as well, then we'll update Q. If E changes, say it was a 1, say it was enabled, and it drops from 1 to 0, we're turning it off, the process will run, but it'll see that enable is not equal to 1, and Q won't get updated. So that's what this is doing for us. It's pretty simple, pretty straightforward. But now that we kind of see what the latch is doing, we get to build the most important block that we're going to talk about today. And a lot of everything is really built off of this. And it's called the D flip-flop. Now, a flip-flop is different than a latch. And it's different in that it is clocked, meaning it only updates the input to the output on an edge of a clock. So here D is basically what we would look like as a clock, meaning at regular intervals, it changes from high to low. This is what your digital circuits know as time. They don't know anything other than a clock is time. And we're going to do it as edge triggered, meaning it's going to happen at the rising or falling edge only. So rising edge is 0 to 1, falling edge is 1 to 0. That's the only time these digital circuits are going to update. How do we do this? How do we make that happen? Well, we just take the D-Latch and make it a little more complicated. So let's introduce a clock. And this clock is just going to feed into these enables. But for the first one, I'm going to invert it. And the second one, I'm going to feed directly into the enable. And then I'm going to take a data input, feed that into the data input port of the first one, and then Q just feeds Q naught feeds into D1. So I can label these D naught, Q naught, E naught, D1, Q1, E1, so that we can stay on the same page. All right. Now, data is going to come in here, and let's say that my clock is, well, I'm just going to draw it actually a little bit. No, I'll start with the 1-0 notation. It's probably a little easier. So let's say my clock starts at 0. Okay, so 0 means my enable 0, enable not is 1. So this first D-Latch is on, and it's transparent, so whatever is happening on D gets passed through to Q0, right? So now we have, let's say we had a 1, this passes a 1, and really, let's make it a little more illustrative, in fact. Let's say that D is just kind of wiggling all over the place. Well, that means Q0 is kind of wiggling all over the place, following it, if I was a good artist, exactly, right? It's transparent. It's just flowing right through. It doesn't care. Well, then the clock rises from 0 to 1. That means the first enable drops from 1 to 0. It's no longer on. That means the output of that latch latches on to whatever that value was, a 0 or a 1, right? I'm pretending like it has lots of values. Really, it's a 0 or 1. But I just want to illustrate. It's just going to take that last point and hold on to it. Then the clock is now passing a 1 to enable 1. So the second D-Latch is now turned on, and it's transparent, but the input doesn't change. The input has no ability to change whatsoever. So even though it's transparent, it's been latched onto. It's locked in. There's no wiggles. So it's going to lock onto that 1 or 0. So when we rise from 0 to 1, at that exact moment, minus whatever the delay through the circuits are, it locks in and holds on to that and remembers it, regardless of what D's kind of doing over here. So if it has a clock signal, and we're marching along here on the clock, and D changes, if D were to change, actually, let me just draw out a timing diagram example. Okay, so let's call this D. Well then, what's going to happen is, and I'm going to write, because I can see people are struggling to see, so I'm going to kind of bounce up above, is Q naught is just going to follow D anytime D is low. Sorry, anytime clock is low. So clock starts low, it's just going to, up to this point we rise. Now here clock is high, so we're no longer following D. We get to ignore it until this point where it drops back low. Because clock is inverted. That's why we're doing lows. And then we just follow D again. Well, we're low here. And then we rise here. So we're going to stop following after we rise. And we hold on to that same value until it falls. We're still at a 1. Okay, so that's Q naught. And sorry, I'm going to have to erase this above so I can make room to finish off Q. So Q1, which is our final output. Now all it's going to do is if clock is high, then we're going to follow Q naught. But what you'll notice is that, so clock is low, we don't really know what's happening here. We don't have a value because we don't have a high clock. So then the clock goes high, we get to follow the Q0, which is high. Now the clock is back low, so we get to ignore it. Clock goes back high, we follow. So rising edge of clock, we get here, we get another 1. Drops low, we get to ignore it until it goes back high. Clock rises, and at this point, rising edge of clock, it's still 1. Well, look, Q1 is just 1 that whole time. Why? Because the rising edge of the clock, is there a red marker anywhere? There's a black at least, I guess, but okay. Rising edge of clock, when it rises here, that's a 1. When it rises here, that's a 1. And when it rises here, that's a 1. So I knew what Q1 was going to do because I know how this functions, because it's a rising edge triggered. It only updates on the rising edge. The D flip-flop. So obviously we don't, every time we write a flip-flop, we don't want to draw that whole circuit. So we create a new circuit schematic. And we're going to see something new, which is this little flag shape or triangle shape called clock. The flag means it is edge triggered. This is what we would call the D flip-flop or the DQ flip-flop. Just like most, the output will have a Q and Q bar. If you wanted to indicate that this was an active low or a falling edge D flip-flop, you would just add a little inversion bubble at the clock. Not surprising, right? So this is the basic building block of memory. This is what we really tend to use because we like to have this edge triggered memory so that we know exactly the moment when we're getting new data. If we don't have this clock, it's a little bit ambiguous, whereas the clock kind of allows us to be synchronous, meaning it all happens at the same time. Now, there's a lot of research and grad level work where you'll see asynchronous designs that will either have different clocks or unclocked circuits that get really complicated. We don't have to worry about that. We're going to stick to synchronous D flip-flops. Now, one of the things that we will do shortly is we'll actually introduce some asynchronous elements into it so you know what those are. Well, let's get that in just a minute.
Can I ask a question?
Yeah.
What is the difference between synchronous and sequential?
Yeah, so sequential is referring to a type of logic that happens in order with memory. Whereas synchronous is referring to the fact that sequential logic is happening at the same time. It is predicted by the rising edge of a clock.
That one was sequential?
That's synchronous.
Synchronous.
So synchronous is a type of sequential logic.
Okay.
Okay. Let's see. We may want to do something like add a reset state for the D flip-flop. Your book will show you schematics for it. I don't think, if I assign a homework for it, it's pretty easy. In the case of the Nand Gate SR latch, if you really wanted to add an additional, like a an external reset state. So this is set and reset, as is traditional for the SR latch. But we could add in one little modification so that when we build it up into the D flip-flop, we can have an external reset that is predictive, and that is just by adding a third pin and calling it reset. That's like the global reset. Because S and R are getting tied into those AND gates, right? So they can't be really used as the reset because they're tied to AND gates out here, right, where this is the SR latch. So these two AND gates feed in. So by adding one extra pin, we have kind of a global reset that we can then use. Okay, well, you don't have to worry too much about that. It's really simple, really easy. But when we convert that and go through all of those same steps, which I'm not going to do for the D flip-flop, you can do something like this. You'll often see it on the top or bottom that just says RST, and very frequent there are active low resets. So all that's doing is saying I can now set this to 0, Q is 0. Now your resets, in general, are very important for sequential logic. And most of the time, you're going to design them as active low. Now, part of that reason is that's just become the industry standard. The other reason is it's actually really beneficial from a circuit standpoint. Because if you imagine a circuit that is, let's say it starts on, right? On means that the reset can be 1 and it's not resetting. But then you lose power and that drops to 0. Well, it turns out that means losing power automatically resets it, right? So when you lose power, it goes back to a predictable, well-defined state from where you can boot up. That means it's reliable to start it up because you know where it ended, right? It makes life a little bit easier to have these active low resets. It also means that you can have downstream error detection if you lose power because they just go to a reset state, which is beneficial. So you'll see these active low resets most of the time. If you didn't want an active low in the drawing, you just erase the inversion bubble and ta-da. You've communicated the same idea. So something else that we like to do is clock. Oh, sorry. This whole time I should have had a, rather than an E, I should have had this clock because I'm talking flip-flops. You don't necessarily need to write the word clock because the flag by itself indicates edge triggered, which means it's expecting a clock. Now, you'll notice that there's a bit of an issue here. Well, maybe not. That now that we have a clock, we don't have the enable, right? Because the clock is acting like our enable and rising edge. But what if we only sometimes want to update the memory on the rising edge? What is something that we do to create an enable signal? What simple circuit do we have that it makes it easy to add an enable? Not sure. So let me rephrase. If I wanted to say, in order to clock D into Q, so let me say that again. So this is kind of the terminology to say. So we would clock D onto Q, is what the clocking terminology is. So let's say I only want to clock D onto Q if I have the rising edge of a clock and an enable. Anyone else have an idea? AND gate. Great.
You have a rising edge to enable and what?
A rising edge of a clock and enable. That's the only time I want to update Q. AND gate. Now, this is kind of the straightforward way of doing it, and it turns out we don't like it. Because there is no obvious difference between clock and enable. So either one can trigger that clock. So you might see if enable dropped early, the clock period would end early, right? So both can generate clocks. We don't really like that. It can cause issues, especially in what we call high-speed designs. This is a bad way of doing this. Look that you know that this exists because we like doing AND gates for enables. In this case, it doesn't work. So we need a way to avoid this problem. We don't want to use what is called a gated clock. This is a problem. Gated clocks are a problem. And in fact, Vhdl will throw you an error if you do this. Well, at least a warning. It'll say warning gated clock. So we leave the clock alone, and instead we come back to our old friend, the mux. And then we just take Q There we go. All right. Now, is this an active high or active low enable? Think about what happened. What happens when enable is 0?
It would do, it send Q through, correct?
Yeah, it sends Q back through. Meaning if the clock happens and we have enable is 0, nothing changes. So is that active high or active low?
It'd be active high, wouldn't it?
Yes, active high enable. Because I need enable to be 1 in order for D to pass through into the flip-flop. So this way we avoid that gated clock problem. We use this feedback to say, well, if the clock happens and I don't have enable, then let's just take the old value. Let's just keep holding on. This keeps it fully synchronous. There's no gating issues. The enable isn't going to cause weird oscillations in our clock. Everything's happy. One other thing that we can add onto this that we'll see coming up is an output enable that we usually label as OE. So this is what we would just call tri-state. So it's a buffer. So it's like an inverter, right? But it doesn't invert. It just passes it through. And what it does is if it is enabled, it passes the value through. If it's not enabled, it goes to high Z, high impedance. You'll hear both of those, meaning it just doesn't drive the signal. This is really useful if I wanted to, say, hook up 2 different memories, 2 flip-flops, to 1 wire. Okay, so most of the times we don't like dual-driven nets, right? Meaning we don't like to provide 2 wires that are being assigned from 2 different spots. This, however, is okay because I have output enable and the invert of output enable. So only one of these is ever going to drive this net F. Right, it's impossible for both of them to be driving at the same time. I'm protected, everything is fine. And just by toggling OE, I can choose which memory to read from. When I draw the DQ flip-flop, then I can just add so here I have an enable, so why not add enable? And then here I'll add OE as a port. So that's kind of what you would do, something like this, where you'd have enable. EN means input enable. OE is output enable. I guess I should specify sometimes you will see, rather than EN, you'll see CE, which is clock enable. That's another notation that you'll see. All right, so now we've got our D flip-flop. Let's do something interesting with it. So this is the simplest way that I can draw a D flip-flop, right? There's no options on it. I didn't bother labeling the clock. It's still a D flip-flop. But I've used this notation before in lab where I turn this into a bus. Now the implication here is that there are 8 wires going into one D flip-flop. Well, no, there's really 8 D flip-flops is the implication, right? And they're just all in parallel, and each one is storing 1 bit of the bus and outputting 1 bit of the bus. But we don't want to draw 8 D flip-flops because that would be awful and annoying. So instead we just use the bus notation. So multiple wires bundled together is called a bus. Doing it this, when I combine a bus worth of memories, D flip-flops, I get a register.
One more time.
A bus worth of D flip-flops, so multiple D flip-flops becomes a register. Okay. The way I'll often write a register is like so. And each one of these cells will have 1 bit of memory in it. So you could have a number like that stored in it. This is what's happening when you're writing, like you have a vector, right? So say you have some output F and you wanted to assign it to vector V at location 2. Right? This is what it's looking at, is it's this register of values in like it's a memory, right? It has a register with the values that has 8 locations in it. And location 2 is, well, we're 0 indexed. So that means the furthest right one is 0, 1, 2. That means in this case, F is 1. It would be flipped. So this is the case of 0, 1, 2, right to left. That's how we tend to think, right? This is the case when you use the 7 down to 0 notation. If you had instead written 7 to 0, oh, sorry, 0 to 7, then location 2 would be this bit instead. So that's kind of why we do the 7 down to 0, is so that the numbers are represented the way we think. The computer doesn't care, right? But it's handy if the computer is acting the way we think it should.
So 7 down to 0 is right to left, and then 0 to 7 is left to right.
Yeah. Yeah, so 7 down to 0 is the way that we write numbers, right? So this is the least significant bit, LSB, and this over here is the MSB, most significant bit. All right, let's talk clock enables and output enables in Vhdl. So when we design this process for the flip-flop, we don't want to react to the data, right? We only want to execute on clock. So that's the only thing I'm going to put in the process sensitivity list. Then I can do conditions. So it says something like, well, let's do a reset and an enable. If reset is equal to 0, then Q gets assigned to 0. This, I'll do the else over here.
All right, RST is reset, right?
Yeah, RST is reset. So if reset is 0, then Q gets assigned to 0. Otherwise, Q gets assigned to D. Okay. Is this an active low or active high reset?
Active low.
Correct. Active low. If the reset is 0, we're just setting it to 0 so we know what happens. Otherwise, Q is equal to D. So if we're not resetting, Q equals D. If reset is 0, this second half of the if statement never executes, right? This is an else. If this is true, the else never happens. Now, I have intentionally made a problem here. So what is the condition? So this executes on, well, I'll ask it as a question. When does this process execute? What is the description I've always used? Okay, so it executes when clock changes. Does it have any way of knowing what that change is, 0 or 1, or 1 to 0? Notice there's no trigger for rising edge, right? It's going to execute on a 0 to 1 or a 1 to 0. It executes whenever clock changes, regardless of direction. So we need a new term. And we'll do that. I'll just push the process up here a little bit. And it just is as easy as saying if rising edge, so the process is still on clock, of clock.
Because previously it was changing anytime it went 0 to 1 or 1 to 0.
Correct. Yeah, so now the first thing that happens when this process executes, so it's going to execute every time that the clock changes, but it's only going to update Q if it's a rising edge. And all I have to do is rising underscore edge. You can also do falling underscore edge. Both of those are valid, they both work, they're great. You'll see me a lot of times in order to save time on the board, just write RE for rising edge. So this line, I would just write RE clock. Just shorthand as I go forward. I start out trying to write as best as I can for the code, and then I'm going to simplify. So that's what RE means. FE is falling edge. Okay. Now, yes.
Yeah, anyways, I was gonna ask, so do you only need an end if it's multiple lines, so if it's just one line?
I do need this as well.
You do need, okay. Cool.
Yeah. So in the corner, sorry, I don't know your name. Is this a synchronous or asynchronous reset?
Synchronous?
Synchronous reset, because it can only reset if rising edge of clock. Let's go ahead and build it into an asynchronous reset. The first thing that we do is we add reset to the sensitivity list. That way we can respond instantly to it, right? And then I just say if reset is equal to 0, then Q gets assigned to 0. Okay, now we get to introduce the else if statement. And Vhdl is kind of annoying with this because in the else if, they get rid of the E in else, the second E. So it's else if. Because we don't want to say else, right? Because if you have if else, then the other one will always execute if it's not reset. Because we want an else if rising edge of the clock, then and then you have end if, end process, etc. Yeah.
So this code doesn't use the enable at all, correct?
This one is not using the enable. You could, if you would like, embed you can also, it is also allowed, I don't like doing it with the rising edge, but you can actually have multiple conditions, which you could write if rising edge of clock and 0. I recommend against doing this for the rising edge condition because the errors get weird on this one. If you've done like a gated clock or something and it starts throwing errors, when you see the error, if the enable is on the same line versus being kind of embedded, it gets harder to hunt down. I don't mind using multiple conditions in other situations. I just recommend it against it in rising edge. Okay, we're just about out of time. Let me that. Oh, it's also really important that inside of a process, never use more than one rising edge or falling edge statement. You only get one per process. You can have multiple processes inside the same architecture, but do not have multiple rising edges inside of a single process.
So this just means you won't have more than one clock. Is that what you're meaning?
Yeah, so don't do don't do that. It doesn't do well. We call it the clock tree, which is kind of how the clocks branch out. And it might execute, but it gets really confused really fast. So trying to make sure I'm okay on serial. I got like 2 minutes. It's fine. We'll start off next with an application of the flip-flops, which is what we call clock division. So the clocks that we use are going to be labeled as something like, they're going to have a speed. And it's going to say something like 10 kilohertz. So that means 10,000 times, and hertz is a unit of per second. So that's 10,000 per second. That relates to time in seconds by t, the period, is equal to 1 divided by f, the frequency. So let's draw a clock real quick. This is how many times it happens per second, right? But the distance between two rising edges is the period capital T. The frequency is related to that in an inverse manner. This is the only way a digital circuit knows what time is. That's why you can't say write 10 nanoseconds. It doesn't know. But what you can do is count the number of clocks. Wait for 30 clocks, right? That you can do. You have to do that conversion, and we'll talk about how do we kind of make different clocks, how do we adjust the clocks. Mostly slow them down. 3610, we'll talk about speeding them up because that gets harder. But anyways, this is where we're going next. Thanks for listening. I know some of you expressed interest in office hours. I will be in my office hours for the next hour and a half. I have to cancel my afternoon one today, but I'll be there for the next hour and a half if you need help.
Real quick, can you describe the difference between asynchronous